next presentation is by Ken Campbell. He's going to talk about Campbell and Bozorgnia GMPE. Ken Campbell. I think I've heard that name before. I think we met a couple of times. Yeah, a couple of times. So let me.
So at least it's starting off colorful, right? Okay, so I'm just going to show you some results. We've only managed to get the minimum deliverable for the November 12th deliverable to CEA and the USDS, which was the PGA and spectral values at 0.2 and 1 seconds. So I'm going to show you those results. I don't have response spectra to show, therefore. But anyway, so the contents, I'm going to just explain our data selection criteria. And then changes from our 2008 model, and then some example residuals, not nearly as many as John just showed, but just to give you a flavor for how well the model is fitting the new data set. And then a comparison of the new model with the 2008 model. And then, since obviously with only 3 periods, you know we're not done yet, so work to be completed by the project end at the end of January. So the data selection criteria, in essence, we have magnitude 3 to 5.5 data from California events only. I think this has been covered, so none of this should be too strange. We're just going to focus on what we specifically applied for our data set. And then 5.5 to 7.9 concludes California and global events. We require that there be a known focal mechanism or a fault type in order for it to be included. And we included class 1 events using the, sorry, I have delta RJB here rather than CRJB, but it's the CRJB 10-kilometer criteria. And then for the sites, only free field sites, but this did include not only just instrument shelters, but it also included non-embedment buildings. John Stewart, as well as Bob Darrow and I 30 years ago, discovered that if the building wasn't embedded, really, it didn't have much impact on the ground motion. So we've continued to use that criteria. We require that there's known or estimated via the proxies that John talked about this morning, VS30 values, and as we just heard, limited rupture distances to 80 kilometers. And this was to look at only geometric attenuation. What we discovered right away, and this is a big issue, is that there are big regional differences in anelastic attenuation. Japan attenuates much more rapidly beyond 80 kilometers than does California, which attenuates much more rapidly than, for example, Wenshan, China. Okay? But we found that if we looked at 80 kilometers, all of those events are fine. There's no systematic difference in attenuation at that point. So this is kind of a nice observation, is that I think that geometric attenuation is pretty much constant around the world. And so this makes it a lot cleaner. We can do an analysis that's not regionally dependent to begin with, and then add an regionally dependent anelastic attenuation terms. As far as number of recordings, to get reliable estimates of the event terms, we required that for magnitudes less than 5.5, that there be at least 9 events within 80 kilometers. Between 5.5 and 6.5, at least 3 events within 80 kilometers. And because we have limited data beyond 6.5, we're allowing only 1 recording for magnitude 6.5 and greater. So on the left is our 2008 database. You can see it basically was only between 4 and 7.9, which is Denali, which only had a few events, really. On the right, then, is the new selected database. So this is our actual database that we're using. So the big difference, of course, is at small magnitudes where we have all that data, but also filling in, particularly in the 6 to 7 or 7.2 range. Still, we're lacking data above about 7.25. And interestingly enough, because we haven't concentrated on this zone, basically between 5.5 and 6, you can see we're a little light there. I think we need to try to fill in that area. Now this is just looking, that was in log scale distance. This is looking in linear scale distance, magnitude and distance. So you can see that actually there's a nice uniform pattern there, except for the gaps that I just mentioned. I'm not going to show you our equation. It's been published. It's been out there for 4 years, 5 years. So I'm going to assume everyone is familiar with our model. So I'm just going to explain the changes. And one of the changes required because of the small magnitude data was that we had a trilinear magnitude scaling term. So with hinges at 5.5 and 6.5. And now with the small magnitude data, we found we had to put another hinge at 4.5 to capture the magnitude scaling. And this then eliminated the over-prediction that we were getting at small magnitudes, well, that everyone was getting at small magnitudes. We've adopted the Jennifer's hanging wall model, but again, only over the rupture plane. Well, actually, we allow it to go beyond the rupture plane, but then we impose that distance taper that we had off the rupture plane from last time, which really just dampens it out very quickly. And we found that we had to do that, otherwise we got biased residuals. And I'll show you those residuals now. Actually, they look very good. The model works very well over the rupture plane, and probably just off the rupture plane a little bit. It peaks over the bottom edge of the fault, whereas our old model peaked over the top edge of the fault. And so others had discovered that. We hadn't. We didn't include Rx as a parameter previously, and now Rx is in the model, which allows that trade-off between Rup, which wants to decrease away from the top edge of the fault, and Rx that wants to bring the hanging wall effect back up. And I'll show you the impact of that. And then we have a hypocentral depth term. Sorry, Norm. The second term here, we're willing to, if hypocentral depth is a big problem, we're willing to look at ZTOR as a proxy. But we did look at both parameters, and hypocentral depth, even for the larger earthquakes, did a better job at predicting the depth effects. And in essence, it starts increasing beyond a 7-kilometer hypocentral depth, which I think 7 is about the average depth of an earthquake in California. The fault mechanism term is no longer depth dependent. We had, for the reverse faulting, we had buried versus surface rupture. And it's no longer, now that we have this hypocentral depth term in there, and this new hanging wall term that captures the hanging wall effects better, we found that the mechanism term did not need to be depth dependent anymore. And we did find it goes away at small magnitudes, as others have noted. We did find the dip of the rupture plane to be important, and again, this was important at small magnitudes, oddly enough. Very strong fact. So mechanism didn't seem to be important, but the dip of the rupture plane was, but that goes away at large magnitudes. And then for the shallow site response term, we did retain the Walling model. We looked at residuals. We tried to implement Ronnie's new model, and we got some effects that we just didn't have time to understand. And yet we found that if we just continued to use the Walling model, that we got no bias for for soft sites at large rock ground motion values. So that, and I'll show you, well, actually, I don't have that plot in here, and I'm sorry. Last night when I was working on this, I forgot to put that plot in. We did find a different linear dependence, meaning just the slope with VS30 for Japan, but we found it was bilinear, and so with a hinge at 200. So if we allow this hinge at 200 meters per second, then the slope actually doesn't go flat or increase, as others have found for Japan, to the higher velocities. It still decreases with velocity, but with increasing velocity, but the slope is different than we're finding for California. So there are definitely regional differences there. And then standard deviations, if we just look at magnitude greater than or equal to 5.5, we're getting standard deviations that are very similar or a little bit larger than we got in 2008. But it gets quite large for magnitudes less than 5.5, maybe going up to maybe 50% larger. We haven't included that yet. We didn't have time. We know that delivery to the USGS to run hazard, magnitudes less than 5.5 aren't important to the hazard. And so we tried to at least produce a model that the USGS could use to show some hazard results in December at their workshop, and not worry about those elements at this point that we didn't need to worry about for that purpose. So here's some residuals. So here's this is the between event residual versus magnitude. This is the quote-unquote source term. The red dots there are the Japanese earthquakes. When we first included them, and this is before we recognized the attenuation, the regional attenuation differences, we were getting big differences in Japan. And when we restricted it to 80 kilometers and found that there were no regional differences in attenuation, the Japan earthquakes fell right in line with the others. So we kind of herded them in there and got them in the corral, which was very good. The green one, by the way, is Kobe. The red ones are the three, and the largest red one is Totori, which is known to be a high stress drop earthquake, by the way. So that actually fits quite nicely. Here's again, between event versus hypocentral depth. So you can see, again, this trend is very, very nice. I don't trust those really low numbers because I don't think those hypocentral depths are that good. So there is some error, particularly when you have a plus or minus 2 or 3 kilometer error on a 2 kilometer number. That's not very good. Okay, this is the dip term. So this is after taking out the dip for the smaller earthquakes. You can say we've got basically dip angles down to maybe 20 or even 15 degrees up to 90. Okay, now we're into within event. There's this magnitude. Of course, these are all centered by the event term, so don't worry about that. But I wanted to show it because this clearly shows increase in standard deviation at small magnitudes. And you can say we used 5.5 and greater here, and you can see that's kind of a nice constant, it looks to be anyway, a nice constant sigma. But you get smaller than that, then it starts growing. In fact, we did do analysis in which we just didn't restrict it to 5.5, and I think the sigma did. That's where I'm getting that sigma went up maybe 30% or something like that. So the small events alone are going to have 50% or so increase. So this is again rupture distance up to 80. This is all events. So this is the 3s all the way up to 7.9s. You can see a nice, no bias there. I don't have little bin things in there. I'm not quite as good at doing that as others are doing. But just to show you that the small earthquakes, our model isn't biasing the big ones, of course, because the small have all the data, so they could easily bias it if you don't have their magnitude scaling. And actually, the distance scaling, the geometric term, is a function of magnitude. And if you don't have that, then you can really bias this. But here's the 6.5s and greater, and you can see, again, no bias there. So really, the small earthquakes, the big earthquakes, are all fitting in there. Here, now, here's against the hanging wall term. And so this is what I'm mentioning. You know, if we're using Jennifer's model with the distance taper that we have off the edge of the fault, which is a function of joiner bore and rupture distance, this is the residual analysis. And basically, the high numbers here are basically recordings over the rupture plane, because that's where you are going to get those high hanging wall terms. Because what happens is the minute you get off the rupture plane, that hanging wall term gets knocked down by the distance taper. And so all those zeros that you see there, you know, those are either way off the rupture plane or where the distance taper has just knocked them out. But you can see where they haven't been knocked out, nice trend there. VS30, again, nice. I didn't break this up. Didn't want to show too many plots, but anyway, again, there's no. We normally break these up into pieces and look at them as well. There's no bias. This is our depth. We do have a sediment depth term in there, or basin response term, we like to call it. Depth to the 2.5 kilometer per second shear wave velocity horizon, and this is the residuals from that. And you can see again out to 6 kilometer depth. This has got Japan as well as as well as California in it. And we found that Japan, below a kilometer, or let's say shallower than a kilometer, it did behave differently than California. But beyond that, basically the deeper, in other words, the basins, the real basins, seem to behave like California. We didn't see any bias between California and that. It's just the shallower ones. And I think we're formulating some reasons why Japan is behaving differently at shallow depths and small shear wave velocities. But it's speculation right now, and so you'll have to wait till the report before you hear that one. So here's a comparison of the models. This is strike slip, dip of 90 degrees, and a VS30 is 760 meters per second. And so the solid line is our new model. The dashed line is our previous model. So the blue is 5.5. So basically 5.5 and black and red, that's in the range of our previous model. Basically we are getting somewhat higher ground motions, about 20% higher. This is PGA, by the way, at the larger earthquakes. You can see the green is 4.5. That's the big differences. That's the small magnitude bias that we had before. This is 0.2 seconds. Actually, this one at large magnitudes is almost identical to what we had before. Again, the big difference at small magnitudes. And then this is 1 second. We're actually, at the large magnitude, the opposite occurred now. So we're actually predicting a little bit less. We're getting a little bit more saturation at 1 second than we got previously. Oh, by the way, I just wanted to point out, we've imposed saturation here. Our model also wanted to oversaturate, and we haven't allowed it. So that's why you're seeing, if I point, oops, try not to push it, but pointing right in there. So you can see this is where we've imposed saturation. Our last hinge is at 6.5, so when we impose saturation, basically, we're just not allowing the slope beyond 6.5 to go negative. The magnitude scaling slope is 0 distance. It is horizontal at 0 distance. Now, of course, the minute you start stepping down in distance, then that slope goes up again. So it's only at 0 distance is where we force it not to go have a negative slope. This is interesting. So this is on the hanging wall side. I didn't have time to do the footwall side of this. But this is the hanging wall side. So this is a reverse fault, dip of 45 degrees. VS30 is 760 meter per second. And here, as I mentioned previously, we had a buried and a surface rupture. And so rather than clutter this plot, we've only showed the comparison with our old model at magnitude 6.5, both buried and surface rupture. So that's the dashed black line. Compare that with the solid black line. So you can see what I meant. This is plotted against not RX, but actual rupture distance. So this is the actual ground motion values you would estimate and use in predicting the ground motion. And so you can see the new model actually ramps up a little bit and peaks around the bottom edge of the fault and then dives off. Whereas our previous model peaked at the top edge of the fault and went down. So the big difference is right there in the bottom half of the fault zone. And so that difference is quite large. But you can see from our hanging wall term that our residuals, this model is picking up the residuals quite nicely. So this is 0.2 seconds, similar, and 1 second. Okay, so what we still need to do is we need to evaluate and include the effects of directivity. So you heard what we're doing on that. We're getting help from others on that. We're going to evaluate the new nonlinear site term a little more and make sure we understand why we were getting differences from the Walling model and why the Walling model worked better, at least for our ground motion model. We're going to add regional inelastic attenuation terms, certainly Japan versus California. China, I don't know that we're going to, well, I don't know. Japan and California for sure. I don't know what we're going to do beyond that. We're going to add the additional spectral periods, fill in. We're going to use all 111 to begin with, so we can do smoothing on the regression coefficients. We'll add our magnitude-dependent standard deviation. So, and then of course we develop a vertical ground motion model as well. So, thank you.
Thank you. Very good. Great. Now, questions for Ken. Very nice slides.
Or my co-author. I got to give the presentation. He gets to answer all the questions.
And made the slides.
I have a comment. I'd like you guys to seriously consider having something else than the hypocentral depth, just because for all the users out there, this is going to be a nightmare to use.
We originally included it because directivity was going to be included, and you have to know. Yeah, so we expected that all the hazard codes were going to end up having to put hypocentral depth in there. And so if they did that anyway, then we felt that we were safe using that term. Now, as it turns out, that may or may not happen, so we will look at an alternative Z-Tour model as well. However, I think at this point, we could leave the hypocentral model in there and just give a rule on what to do. Not randomize it, but if you put it in the centroid of the fault plane, I think you're going to do a good job. So actually, in the guidance that we're giving the USGS at this point, that's the guidance we've given them.
If you recall, in 2008, we had Z-Tor, and we examined, as Ken said. I think based on the data, it's better. But if users really strongly revolt against that, we are willing to
But if you have a rule, a simple rule like that, that's good enough. It's just
More questions from Christine from internet?
So Vladimir, man, he has a direct line with this place. So he wanted you to explore or tell us more a bit about the style of faulting and the scaling. So reverse normal and...
Yeah, well, it's a function of period. For the larger earthquakes, the style of faulting factor is in there. We also found a large negative normal faulting factor. I don't think... Well, we haven't looked at all the periods yet, so I don't know whether we go to minus 0.5 like Norm was finding, but we are getting to minus 0.25, minus 0.3 like he was finding. It's not just L'Aquila, as we were really concerned that L'Aquila was doing it. It's not, because in applying the class 1 data, we ended up bringing in some more Italian data. It's also, and there's some Greek data, they're all supporting that lower normal faulting factor. We have found that now that we have a depth term in there, the reverse faulting factor isn't as large as it was. Interesting. We're going in the opposite direction. Norm is increasing it. We're now decreasing it. But it is a function of period. So maybe it's not as strong as the short periods, but it is picking up at 1 second. So again, we need to look at that. And again, once we look at more periods, we'll get to see the trends of these things, and that'll help us decide what to do.
More questions? Yes?
I don't think I need the mic.
You do, because it has to be recorded.
That's the way we record it.
That's the only reason.
There are people on internet.
Yes.
This is just a general question. In Canada, we're just about to put our new code to bed within the next few months. We screwed up our courage and decided maybe to adopt the old GMPEs, the ones that you are now discarding. So
you guys are always behind, so that's
Delete that comment.
Delete that part, yeah, please.
Just remember, imitation is the sincerest form of flattery. Now, do you think all these changes are going to lead to increased or decreased motions?
It depends where you...
Well, do you have any feeling for it yet?
You saw, and granted those comparisons were pretty limited, but you can see that the differences, particularly large magnitudes, are not very large. Now, maybe 20% in PGA at the very largest earthquakes, but that was, you have to be really close. And that was a little bit up. Yeah, that was up about 20%. Okay. But see, once you got out to like 10, 20...
Not 20% G.
No, 20% increase. Yeah, not 20% G, but a
20%
increase in the value.
At one stage in our calculations, our ground motions were going back to what they were when the risk level was 10% in 50 years. 5%. So we've pushed it up a little bit using various devices.
I really think it depends where the location of the sites and also period. As Ken showed it, for 1 second it went down.
Yeah, and any hazard analysis, your hazard doesn't come from something inside of 5 kilometers. It just can't. It can't.
Just be careful not to be late with that January report.
We got other reasons besides you to not be late.
All right, other questions? Yes.
Yeah, Ken, unless I missed it, you're the first one to mention about future work including vertical.
Yes.
I assume by next April, they'll all 5 models will have vertical?
Minimum 3. That's a contractual
minimum
3 GMPs on vertical.
Everyone's committed, or at the beginning of the project, all 5 of us committed to doing verticals because he wanted to make sure that he got at least 3 people agreeing to it.
I learned our lessons from the previous thing, so I committed only 3, but delivered 5 for horizontal. I'm hoping to do the same thing for vertical. Minimum 3, hopefully 5.
Okay, thanks.
More questions? Yes, last question.
Thought I was going to get off the hook from Jim.
Could you shed some light on the so-called regional anelastic attenuation, regionalization?
Mm-hmm.
There are rocks down there, and they have velocities. Is it differences in velocity models?
I think just knowing which regions are showing what trends, it becomes kind of obvious. Japan, as you know, is a volcanic island, right? So the crust tends to be, in some areas the crust is thick and hard. In other areas it's hot, you know, under the volcanic belt. And so I think that you're seeing, and Italy is the same way, right? The Apennines are volcanic. And so both Italy and Japan show strong anelastic attenuation. And they're both come from a volcanic region. The Wentron, it doesn't. It shows weaker anelastic attenuation. Basically, most of the sites are to the, I always get my directions wrong, east of the Wentron area, right? And east, that's considered to be a stable continental region, right? And so we would expect the attenuation to be less there. So at least with our initial ideas of what would be causing anelastic attenuation, what really surprised and pleased me was that if you limit it to geometrical attenuation, you don't see those differences. And that has made our life so much easier because we could ignore anelastic attenuation to work on the model and then add it later. And I think every one of us has decided to use that approach because we all independently discovered you can't throw all that into the pot and get meaningful results out for some of the reasons that Dave Bohr mentioned.
Great. Thank you very much.
Thank you.
We're going to have 10 minutes break. Please come back 3:45.